I'm Baptiste Flipon. I'm working at CMF with Marc Bernacki and Nathalie Bozzolo, and in the DGMU project. The main part of my work is to work with material parameter identification. So here in the context of fuel field modeling, but since we are mostly using the same metallurgical model also in our mean field model, the identification procedure that I will propose to you today remain valid also for that kind of models. So that's kind of nice because we have a kind of really coherent working framework, numerical working framework. So with mean field models, so that are pretty with a pretty low cost in computational cost, and with some recent improvement are also able to give some pretty good prediction even regarding grain size distribution. But those models still lack the explicit description of the microstructure, so it's still a statistical representation of the microstructure in that case. So that is the main advantage of fuel field models. So Marc yesterday already talked about a lot about the kind of models that we are using, and the computational code is called DGMU. So okay, so since we will be speaking about material parameter identification, a little reminder of the equations that we are using. So we are modeling grain boundary migration. So here in a level set framework with kinetic formulation, and the material parameter that will interest us today is the mobility parameter. We will consider grain boundary energy is isotropic and constant and taken from literature from now on. Then we'll describe also strain hardening and dynamic recovery. So here it's a kind of classical formulation with one hardening term and one recovery term. And some equations a little more tricky to describe the nucleation. So I will get in detail when we get to that part. So two questions that we can ask ourselves about those metallurgical models is that how to identify the model's parameter. So it's kind of a wide topic, because we start from experimental tests and how to do them, how to treat the data, the actual identification procedure, and then numerical also validations. And the idea behind that is also to kind of have a reflection about the optimization and automatization of the identification procedure, to at least give some starting point and good guidelines to perform this identification procedure. So this is the outline of my presentation for today. So it will be mainly divided in two big sections. So one section regarding grain growth parameters, and another one regarding dynamic recrystallization parameters. And then I will finish just to show you some work that are still in progress. So okay, so regarding the current identification procedure, we decided to just work with mechanism per mechanism identification strategy. And at first we will take a look at grain growth parameters. So I already told you that we will the parameters that will interest us today is for grain growth is this parameter, the mobility parameter. So here in our model is described through an Arrhenius law. So the two parameters that we have to give as an input for the model are those two parameters, the M0 pre-exponential factor and the QM, that is an activation energy. For obtaining and doing that identification procedure, we will work with experimental data coming from materials that are free of any stored energy. And so we can consider only pure grain growth, so only driven by this capillarity term. So that is the actual procedure for identification of grain growth parameters. So we need at least mean grain size evolution for at least 3 temperatures. And any additional microstructural data is also useful, especially for validation at the end of the identification of the material. So it is really well working with single phase material right now, but the limitations here are really more related to the model in itself and not really in the identification procedure. So the idea for the whole identification procedure is always to start with a good starting point. Okay, so here we use a classical Burke and Turnbull law just to obtain a first value for that product of the mobility with the grain boundary energy, so the reduced mobility, and we get that first estimated value. We compute a first simulation, a first full-field simulation in that case, and then only do a curve fitting of that first prediction of the model regarding the experimental data, just to refine those parameters. So that is what is summarized here. So the first step with the Burke and Turnbull law, so with classical parameter for that law, it's really just to obtain a first value of this reduced mobility to be able to perform a first simulation. Then it will be refined to obtain a second value and a fitted value for these parameters. Those two first steps are repeated at least for three temperatures in order to be able at the end to fit an Arrhenius law on those fitted points. Okay, so that's what we can obtain. So here the result that the fitting part of the Arrhenius law on some previously fitted point on the experimental data that we use, and then some results regarding the evolution of mean grain size. Okay, so in here, so in orange we have what is predicted just by putting the mobility that is predicting by the Burke and Turnbull model inside our full field model. Then the fitting of the points in green, and then by relaunching a new simulation, the red curve gives us the results. Okay, and then now if we take a look, a more comparison look, so both a qualitative one between what predicts the model and what we can observe experimentally with here it's EBSD. So, and all along the one heat treatment, so here it's applied on Inconel 718. And if we take a look also at grain sizes distribution, the results are pretty good, even if in that case, for long heat treatment time, the number of grain at the end become a little low, and we should relaunch those simulations with a higher initial number of grains to get, I think, a better description of this grain size distribution. So okay, so for grain growth parameters, in fact, it's working pretty well on a lot of materials. Since we stay in pure grain growth and with no second phase particle. So we also try to extend that actual procedure for materials with second phase particle, and it's working also pretty well, but we just have to keep away from the solvus temperature of those particles, because at those temperature we will have to take into account in our model the actual evolution of that second phase particle fraction, and right now it's not the case. It was one of the main of the last slides of Marc yesterday, and it shows that it's still in development currently. So okay, so let's move on now to dynamic recrystallization parameters. So we still have our mechanism per mechanism identification strategy, but here it becomes a little more tricky, because we have some equations that are describing several things, and a lot of parameters are in all of those equations. So we kind of ask ourselves how to describe both the correct hardening and recovery behavior, so mainly based on stress strain curve, experimental stress strain curve, and also to be able to predict the microstructural evolution, because at the end that's what we want to do, being predictive regarding microstructural evolutions. So for that we are using two-step and semi-automatic procedure. So starting from experimental data, so stress strain curve for several temperature and strain rates coupled, and also targeting mean grain size. So that first step is performed using the Jonahs method at first. So it's a kind of graphical method based on analysis of the stress strain curve, and especially on performing some derivative and then using them to graphically obtain values for those two parameters, so the hardening one and the recovery one. And then just a curve fitting is made between the experimental points and what predicts at first the estimated value from the Jonahs method, in order to refine those parameters. And at the end of this first step, we don't know anything about the good prediction regarding recrystallized grain size. So that is the idea of that second step, is to take into account also those two equations, and since those two equations can be resolved analytically, we use them in an inverse analysis procedure. So for those who don't know what is inverse analysis, so it's based on initial materials parameters. We launch some, we compute the results predicted by the analytical models, then compare them to the reference experimental data, and if the error is too high, we stay in the loop until that error becomes small enough, and then we obtain the identified material parameter. So at that point we have K1 and K2 that have been identified only on the stress strain curve, and the idea is to find to refine those parameters to also predict the good recrystallized grain size. Okay, so I don't have right now really good results, because you will see in not really good results, but really appealing things to show you on that part, because you will see we are still working on the nucleation rate, in fact, so I will go back to that. But for dynamic recrystallization parameter, and especially hardening and recovery 1, the identification procedure is kind of okay, but still needs some validations and needs to be applied on other materials. So right now we mainly work with 304L and Inconel 718, but it still needs some validation more. And also thinking about thermomechanical conditions, because especially when we will be dealing with high strain rates, I think we will have to reiterate on the identification procedure as well, or on the models. And so one of the actual limitations of that part, I think, is the DRX model that we are using right now, and some new models. And it's also kind of one of the interesting thing about that work is that it will also show some actual limits of the models that we are using regarding a lot of thermomechanical conditions or different materials. So it's also a way to, at some point, take a step back, iterate on the models that we are using, and then try to re-identify the correct parameters. And so I was speaking about some work in progress. So we are working, so here we have the equation of the nucleation rate that we are using currently, and we are working to get that kg parameter in that part of the identification. And we are also using, just as before, an inverse analysis procedure, but at that part we will use not analytical model for here, but the semi-topological mean field model that is developed at CMF. And here we will work with recrystallized fraction evolution for the experimental data that are needed to identify those parameters. And just all those developments are also kind of implemented in a little tool that is developed, and so it should provide some really guided procedure and guidelines to identify material parameters with the right experimental data. So yeah, thank you for your attention.